Hello, everybody. Today we are going to be talking about the column space of a matrix. All right. So we talked last time about the null space. And let's just remind ourselves that was solutions to AX equals 0. And when we say solutions, we mean things that get plugged in here for X. All right. Now the column space, if A is an M by N matrix, it's the set of all linear combinations of the columns of A. And let's pretend we're in class for a minute. What's another name for the set of all linear combinations of something? And I'll pretend you all said span. Okay, so another way to put it, another way to think about it is the span of the columns of A. Okay, and let's think about this for a second. So with the null space, right, we're talking about solutions to something. You have to solve to find them. They go right here, okay? And with something in the span, okay, when we're asking if something is in the span, like we are on this example, determine if U11,6 is in column space of A. Did I give you a matrix A? No, I did not. Okay, you guys, we're gonna play it risky, and I'm just gonna give you something. Okay, 4, 3, 1, 0. Okay. So here's our matrix A. So what we want to know is there a solution to this equation? Can we fill in these blanks and end up with 11/6? So in null space is the solutions, but in column space is not the solution, because the solution is the things that you find to go here. So the column space is sort of the B on the other side. And let's remember, how do we figure out how to do this? Well, we solve. So to do this, okay, we see if AX equals U has a solution. So if there's a solution, then it's a yes. If there's no solution, if it's inconsistent, then there's a no. Okay, let's see how this goes. So we're going to take our matrix, augment it by 11/6, and we don't particularly care what the solution is. We just want to row reduce enough to see if it's consistent. Right, so all we're asking is this vector a linear combination of the columns of A? To do that, you row reduce. So again, just like with null space, we're talking about something that we've done before, right? Linear combinations in solving systems, but we're just putting it in a new context of column space, vector spaces, subspaces, that type of thing. Okay. We'll come back to the subspacing in just a second. For now, we're just going to worry about this. I am going to use the 2 to clear out the 4. So let's do -2 times row 1. That'd be -4, -14, -2, -22. And then we're going to add those together. It's going to give me my row 1. Stays the same, and then -4 and 4 is 0, -14 and 3 is -11, -2 and 0 is -2, -22 and 6 is what? -16. Okay, and that's actually all we need to do, because this is in echelon form. We can see here's a pivot and here's a pivot. Okay, and we see that we don't have one of these inconsistent rows. Okay, so this is enough information to tell us that this system is consistent. Our vector 11, 6 is a linear combination of the columns of A. So 11, 6 is in the column space of A. And that's all we have to do. Okay, so to figure out if something is in the column space, row reduce. This means you row reduce. Okay. In the last video about null space, we talked about how to get a spanning set for the null space. But with column space, a spanning set is built in, right? It's the span of the columns of A, so we know exactly how to get the null space, we know exactly how to get the column space. You take all the linear combinations of these three columns. Okay, let's talk a little bit about one more theorem. Let me figure out, for those of you actually in my class, it's theorem 4.2.3. So this is, we have A is an m by n matrix, and here we have that column space of A is a subspace, so it's got 0, it's closed under addition and scalar multiplication. Column space of A is a subspace of some dimension of R, and let's talk about which. So we have our matrix A, which is an m by n matrix, okay? And then what we're wondering, right, the column space, the things that end up as linear combinations are over here. So this is something that's in the column space, okay? To be able to do the multiplication, this has to be n by 1. That was the dimension of the null space, and then what you end up getting is these outer dimensions, m by 1, right? If you take a bunch of things with m entries and scale them and add them together, you're going to get m entries. So this is our m. We are not going to prove this, but you are responsible for the null space proof. Okay, that's going to be it. So we'll talk more about null space and column space some other time.